I believe we are ready to start our lecture number 9. And as usual, I'm happy to see so many faces still surviving till this very large number of lectures. And as usual, we will first recall what was said last time in the end. So the topic is the quantum Hall effect. Quantum Hall effect. This is not the pen. Quantum Hall effect. And as I said last time, a crucial thing for the quantum Hall effect is disorder and localization. Without any disorder, we do not expect Hall conductivity to be quantized, because there is a Galilean invariance that tells us that each electron contributes the same amount to the Hall conductivity. So quantum Hall effect is the dependence of sigma xy Hall conductivity on the concentration of electrons. This is very important that we have concentration here and not anything else. And as a function of concentration, we have some steps here. These steps occur at integer values of e squared over h. This is 1, this is 2, and so on. This is 3. And the reason behind this picture is the picture of the density of states as a function of chemical potential now, mu, density of states, rho, well, of mu. Then. So the density of states in magnetic field is a collection of delta functions which are called Landau levels. These are Landau levels. So within this picture, when we have Landau levels, it's not enough to have quantum Hall effect. We should add some disorder here, Landau levels plus disorder. And the effect of disorder is the following. First, it makes every Landau level, it gives some thickness, so it's a whole, if you like, band, some energy window with all these states. These are all available electron states. And another effect of disorder is that all these states are actually localized and they do not contribute to conductivity except for a single state, which is in the middle of the Landau level, right here at the energy in the middle. There is one specific state that is not localized. So as you fill this spectrum with electrons, you increase the concentration, you first fill localized levels and conductivity does not change. And then as you reach this center of the Landau level and you feel this specific single state in the middle, you have the jump. And then you continue filling all the localized states and sigma xy does not change. So this red one in the middle is, it's red, right? This one red in the middle is delocalized, is the only state that is not localized. Delocalized. Also in the middle of this one and the middle of this one, but all other states are localized. So this is just a claim how things work. And to prove this picture, to prove that there is a delocalized state in the middle. There are various ways to do this, and since my lecture course is mainly about nonlinear sigma model, I will tell you how the nonlinear sigma model works in this case, and how we usually can describe quantum Hall effect using nonlinear sigma model. So just as before, we have the nonlinear sigma model, which is the following action. This is unitary class, that most simple model that we originally derived, and which is the model on the with the Q matrix that belongs to the coset space U of 2n divided by twice un. And the Q matrix can be represented as the rotated matrix lambda. And T is just the unitary matrix. So the action is an integral over the two-dimensional space. Now, quantum Hall effect is a two-dimensional effect, so it's a two-dimensional integral, trace, and the coefficient here, it was originally pi nu d divided by how much? By 4. By 4. And then gradient q squared. So I will rewrite now this prefactor here as it's pi nu d over 4. I will instead write sigma xx divided by 8. Just a side note. This is the board for side notes. It's not recorded, so I can write anything here. Sigma xx, it's just the usual conductivity, is E squared nu d, right? This is the Einstein relation. And the coefficient we have there is pi nu d over 4, which is sigma xx, this thing, times pi and divided by 4 times E squared, right? So I will also add h bar here because I usually omit it, and then this is 2 pi h bar sigma xx divided by 8 E squared. And 2 pi h bar is just h without bar. So this whole thing is sigma xx divided by E squared over h divided by 8. So what's written here is dimensionless conductivity. It's sigma xx measured in units of E squared over h. In this particular units. And in most quantum problems, it's quite often easier to measure conductivity not in inverse ohms, but in these quantities. So this is sigma xx over 8. And we should do something to this model such that it describes quantum Hall effect. And what exactly should be done was actually discovered in the beginning of 80s or closer to the middle of 80s by a guy. I will right now tell what guy. So to describe quantum Hall effect, we should add an extra term to this action. And this extra term looks like this. It has another coefficient, which is now sigma xy, the whole conductivity, this one, measured in the same units. So it's just 1, 2, 3, 4. divided by 4. And here is the following combination. Q nabla x, Q nabla y, Q. And this is the end. This is the action. This thing here, which we have just added, this thing has many names. Usually it's called theta term. And as I said, it was first proposed in the context of the sigma model. It was first proposed by a guy named Pruisken. I believe it's written like this. It's a Dutch name. If anybody know how to read Dutch, they will tell me it's Pruisken, actually, not Pruisken. Adrian Pruisken, around 40 years ago, first derived this term, and theta term is the name because the coefficient here, the Saichi term also occurs in some other field theories, namely in quantum electrodynamics. I believe you can also add it, and in that context it's called theta term because the coefficient is theta and not sigma xy. So this term, yeah.
Other ways we have to add some extra terms.
Very nice question. We are allowed to add any terms we like, provided they have not more than 2 gradients inside. And so, see, there are 2, 1, 2. There are also 2 here. If you add something with 3 gradients, this is not allowed because it will be irrelevant. I mean, it will scale to 0 in the RG equations. So you can add something which has not more than 2 gradients, 0, 1, or 2. You can add something that obeys all symmetries of our model. So it should be written in terms of the Q matrix. It should be a trace of some product of Q matrices or a product of traces. And it also should not be identically 0, because if you add an identically 0 term, it does nothing, right? So it depends on which class you consider. This term can be added in the unitary class in 2 dimensions. If you do the same in 3 dimensions, it's impossible because who is x and who is y in 3 dimensions? I don't know. Or in 1 dimension, it's impossible because in 1 dimension you have only x. So this can be added only in 2 dimensions, and in unitary class, because if you do the same thing in any other class, for example, you can write the same thing in orthogonal class. But then it will turn out that this is identically 0 because Q matrix belongs to a different space, and I will prove it right now. So we will analyze this term right now, and we will see that for unitary class it's not identically 0, but otherwise it's almost 0.
Can I add some combination of random function of Q?
Random what?
Random function of Q with some gradients or any other stuff.
Yes, you can, but since this is a symmetric space, you should keep in mind the following fact, that Q squared equals 1. So if you have any function of Q, you first write it as a power series, and then you immediately see that this power series has either a constant or just single Q.
At the last lecture, we saw an example when Q squared is not 1.
Right, but it was in a different class. I mean, in this class, you cannot add a function because Q squared is 1. That was in the chiral class. In the chiral class, Q and Q inverse are 2 different matrices. But then, in that chiral class, there is a similar condition. You can add a trace of any function, provided that you interchange Q, Q inverse Q, Q inverse Q, Q inverse.
Okay. And now we are in unitary class, right?
Yes.
But there is a magnetic field.
Yes.
So it's rho times symmetry.
Yes, that's why we are in the unitary class. Unitary class has no symmetries. All symmetries are broken.
Why we haven't had this term when we initially described the sigma model? Because it's also
because we are not as smart as this guy. First of all, and second, because we derived this action, we did the derivation starting from the Hamiltonian, and this term did not appear. Now, what this guy did, he did the same derivation starting from the Hamiltonian, but with magnetic field in this Hamiltonian. So if you redo the whole derivation for a Hamiltonian with magnetic field, you will find this term after another 5 lectures of derivation. It's a really hard task to do. I mean, but we are lucky because we know symmetries. So we know our Q matrix is of this form, and there are not many terms that you can think of. So this is quite a rare occasion when you can add an extra term. Yep.
I have two questions. The first question is that if we consider two-dimensional material, we mean that 2 dimensions is very thin 3-dimensional, right?
Yep.
So if I be slightly increasing size on the z-axis, our model will be less and less applicable. So how can I estimate what is the thickness of this z size, and how will model break if I increase this thickness?
So this is for exactly 2-dimensional model, and quantum Hall effect is observed in a 2-dimensional electron gas, which means the following. The z direction is fully quantized. Your electrons are in a potential well in z direction such that there is only one quantum state as a function of z. So you have your wave functions are basically some fixed function of z times whatever you like in xy plane. So it's strictly 2-dimensional. There is no third direction. Now, if you want to study something of finite thickness, you can start with this model, and you can stack several of them, one on top of the other, and introduce some coupling, and whatever can happen in that situation, you can. It can be studied, but it's not in this model right now. So for the quantum Hall effect, we just want a strictly 2-dimensional model.
Second question is that, like, we want to describe quantum Hall effect, and we write this model basically from our previous understanding of sigma model and from some extraordinary intuition about theta term. But how can what do we think about the physics when we write this model? Because for me it's not obvious that I can start with this model.
I will show you some consequences of this term, how it works. Maybe then the intuition will become better. I will also show later some alternative view of the quantum Hall effect, more physical, which leads to the same model. So you will see this. So theta term, we should do some calculation because so far I'm just making claims. This is correct, that one is wrong, this should be written like this. I understand such claims are not very productive, I mean, for educational purposes. So let's analyze what this thing actually does. And in order to analyze this, we will take this formula for the Q matrix, this, and put it inside and see how this term actually looks as a function of t rather than a function of q. This is very instructive, actually. So what is the gradient of q? Just any, maybe x, maybe y, in any direction. Gradient of q is the gradient of t inverse lambda t, right? And this is a derivative. It can act either on t or on t inverse. So this is t inverse lambda gradient t. This is when I act on the last one. Or gradient of t inverse lambda t. This second part here, the gradient of the inverse matrix, we already saw it a few times. Gradient of the inverse matrix is minus t inverse gradient t inverse. And then lambda t is before. So I can rewrite the second term in this form. And when I do this and look at what I have t inverse on the left in both terms, here and here. So I can write t inverse times something. take this common factor out. Then from the first term, I will have lambda gradient t. I believe the board is about to end, so I will extract it. And then, just for some, okay, and that's it for now. And from the second term, I will have minus gradient t, t inverse lambda t, right?
T outside the bracket.
T inverse is outside the bracket. So this is the first term, and T inverse times this is the second term. And yeah, I would like to also take this T outside to the right, but here I don't have it, I have gradient of T. So I will insert here a product T inverse T, which is just a unit matrix. I will insert it as a factor at this point. And then this whole thing becomes T inverse lambda gradient T, T inverse minus gradient T, T inverse lambda, and I can take the other T outside on the right. Yeah, so this first part is this one with T inverse T, and the last one I just took T outside. And finally, this same thing is T inverse. What I have here in brackets is a commutator of lambda with gradient T, T inverse. And then another T to the right. So I probably can squeeze this a little bit. Yeah, so gradient of Q equals this thing. This is just the exact rewriting of this object in terms of matrix T. And actually, this was one of your homeworks a few lectures ago. Remember, when we derived the sigma model, we get something in terms of the matrix T, and I told you this equals gradient Q squared. So this is how it can be checked. Gradient Q is that thing, you just square it, and you will immediately see the identity that we had that time. So gradient of Q is this. Now what is this object here? Let's see. Theta term contains the following trace. Now it's trace Q nabla XQ nabla YQ. So let's write it. Trace, this first Q is T inverse lambda T, right? Gradient X is this thing, T inverse commutator lambda with gradient X, T inverse T, times another gradient, which is T inverse commutator gradient Y, T inverse T. This is Q, this is one gradient, and this is the second gradient. So obviously what I do, I just cancel T and T inverse, these two, and this one with the first one. Yep. Under trace I can do such things. So I have lambda, one commutator with lambda, and second commutator with lambda. That's very easy. I have in total 4 terms. Each commutator has 2 terms inside and 2 different orders. And this has 2 different orders. So I have 4 terms in total. And this thing I will do without writing them all explicitly. And then we will discuss and find that this is really obvious. So I have lambda. Oh wait, no, let's do it like this. I have gradient x t inverse lambda gradient y t inverse. This happens when I just remove this commutator brackets and I say lambda times gradient times lambda times gradient. Lambda squared is 1, it disappeared. Then there is a gradient, lambda, another gradient. I can also flip both commutators like this. Then I will have lambda, gradient, lambda, gradient, lambda. I will have twice this term minus, when I flip only one of them, I will have lambda, gradient x t inverse, gradient y t inverse. So I claim that there are 4 terms in total if you open these brackets, but actually there are twice this term and twice this term. So these are the 4 terms. And to see this, you maybe have to do some cyclic permutation and trace, like taking this lambda and put it in the end. So I always have these 2 gradients, x then y, and then lambda enters either between them or on one of the sides, and 2 other lambdas cancel out because lambda squared is 1. So the last thing, I will write it like this, minus 2 trace lambda times a commutator of gradient x t inverse with gradient y t inverse. That's all. And the very last way of rewriting this thing is the following. It's minus 2 rotor trace t inverse lambda gradient of t. So, some explanation. This is a vector. Nabla is a vector. It has 2 components, x and y. Rotor of a vector in 2 dimensions means x derivative of the y component minus y derivative of the x component. It's just like a 3-dimensional rotor, but only its z component. And if you apply a second derivative, so rotor is some derivative of this object. It's no need to take twice the same derivative here, because how should I put this?
Rotor of gradient is 0.
Rotor of gradient is 0. Yeah, that's a nice point. Yeah. So when I say rotor, it means that the gradient should act only on t inverse from here, and then using this identity for the gradient of t inverse, you will just reconstruct this commutator. Yeah, it's a simple exercise. I mean, if you don't believe, you can just do this. X gradient of y component minus y gradient of x, and you will have 2 terms, and they will be exactly these 2 that are inside the commutator here. So, coming back to your question in the beginning, why do we at all care about this Pruskian term? It's not really obvious, because the object that stays here, this trace, is a total derivative. It's a rotor of some vector. Yeah. So the integral, now the integral over two-dimensional space of this trace q nabla x, q nabla yq is the integral of this rotor. So it is -2 and then an integral contour. I don't know why I write it contour. Sorry, just an integral over gamma, over the boundary of our two-dimensional space, ds times this trace, trace of t inverse lambda gradient t. Yep, you have a two-dimensional sample. This is our sample. And we had some Q matrix which lives inside and is defined at every point. It's the function of two-dimensional coordinate. And then it turns out that the integral of this combination of Q over the whole area equals an integral that goes only around the boundary in a certain direction. So it's a circulation of this. This is now a vector. This is a two-dimensional vector. And our term is the circulation of this vector along the boundary. So in a sense, if we have an infinite sample, the boundary is very far away. Nothing happens there. Q matrix is some boring constant. This should probably be just 0. Probably. I mean, we added to our action an integral of a total derivative. As we all know from whatever classical mechanics, adding a total derivative to the action doesn't change anything. So on the first glance, this term shouldn't change anything. And actually on a classical level, if we consider this sigma model action as a classical action, we can derive equations of motion. This term will not contribute to any equations of motion. So to say, if you take a variation of the action, for example, you found the minimum of the action, and then you take the variation near this minimum, the variation of this term will be identically 0. Because it's a total derivative. It's an integral of a total derivative. But there is another caveat in this thing, not a caveat, another property. It's a total derivative, but it's not it is written not in terms of the Q matrix. It's a total derivative, but written in terms of the matrix T rather than the matrix Q, which means this term violates gauge symmetry. I mean, gauge symmetry is something, it's a symmetry when you change matrix T such that Q is not changed. So Q is our gauge invariant field, and T is a larger space, it's a group, and we can have different T's that correspond to the same Q, so we can change T somehow. This term will change because it's written in terms of T, but Q doesn't, which means the action should also not change.
The integral can keep the same.
Right. This is a good point. The situation, for those of you who know, the situation is very similar to what happens with the action of electrodynamics. Electrodynamics is a gauge theory. There is an electric field or magnetic field, or the tensor, electromagnetic tensor, which is an observable object. And then there is something like a vector potential, which is not gauge invariant. Gauge transformations change vector potential without changing any observables. And you can write, and the action of electrodynamics is written explicitly in terms of the vector potential. I mean, the action when electromagnetic field interacts with matter. This term of the interaction is written explicitly in terms of the vector potential, And then you can prove that applying a gauge transformation to this action changes the action, because it's not gauge invariant, it changes. But this change is a total derivative. So it doesn't change any equations of motion that, or any observable quantities. Well, okay, so let's look at this term and ask the following question. What happens if I have my sample and this sample is infinite? It's a two-dimensional sample, well, not literally infinite, but just very large. And we do some measurement of conductivity, of Hall effect, we apply magnetic field, whatever, in a limited part of the sample, and then it extends to much larger distances. And this Q matrix, somewhere far from our point of view, is just a constant. Nothing happens there for some reason. I mean, no matter why, but let's assume just for a moment that Q equals lambda at the boundary of the sample. Boundary of the sample is somewhere very far, and actually the value of Q should not really matter. So we can fix it to any matrix we like. For example, lambda is just one point of our manifold. Why not fix Q equals to lambda at the boundary?
It should be more or less constant, but because the gradient it decays with like 1 over L.
Sorry, what are you now talking about? What should be a constant?
The impact of this term.
Oh,
integral term.
the impact of this term we will right now analyze. So Q matrix is constant. It's the usual assumption, you know, for example, also in electromagnetics, when you say we have a charge, it creates a field, we always assume that this field decays at infinity. Yeah, we have field, we choose it such that potential is 0 at infinity, so whatever happens in our physical part should not go to infinity, or at least without a good reason. So we assume that all these gradients of Q, they're finite here, but they decay, that they get small at large distances, and Q is just some number, some fixed matrix. And actually lambda is just a simple choice. We can choose any other point of the manifold, doesn't matter. So Q is lambda, but T is not fixed. That's the point. Even if we say that the matrix Q is 0, or its lambda is fixed far away, it doesn't mean that we fix the T matrix. For example, if you have magnetic field which is bound to a, it's an example, I mean, it's not, it will not be directly needed. If you have some solenoid, a thin object, a thin stick with a wire winded on it, you apply electric current, you have magnetic field which is inside this solenoid, you have a magnetic field inside, and there is no field outside. But if you write vector potential will circulate also around this thing. It will decay at infinity, but it will exist outside of your solenoid. Because this vector potential is actually not gauge invariant, so there is no field. If you take the rotor of this vector potential, it's 0. Still, it will exist even outside. The same thing with this T. Our Q matrix, our real things, they happen only in some specific part near our eyes where we look, but the matrix T can do some nasty things even at infinity, provided that Q is still lambda. So it's like the gauge field, it's like this vector potential. It can do whatever it likes, as long as it doesn't change the matrix Q, all is fine. And since we all remember that Q is T inverse lambda T, yeah? Q is this. And I want it to be equal to just lambda at infinity. What can I say about the matrix T? Matrix T at the boundary of my sample should have the following form. It should be block diagonal, should be retarded and advanced parts, but nothing here. So if matrix T is log diagonal, then T inverse lambda T will be just lambda.
So you say that let's create some kind of perturbation deep inside the sample, and we assume that it somehow will go to zero somewhere in infinity, and that's it, right?
Not really a perturbation. Look, with this action, what we do, we just sum over all configurations of Q, and this action tells us what weight in this sum should we take to get the partition function. So I say we sum only over configurations that do something interesting here, and a Born constant at infinity.
Okay.
This is our boundary conditions, if you like. Q equals lambda is our boundary condition.
Okay.
And yeah, that's it.
Okay, I was okay, I got the problem.
So Q equals lambda at the boundary. T at the boundary has this form, and this trace here that I have will be minus 2, the circulation of, minus 2 integral along the boundary, the circulation of the vector which is trace of T retarded inverse gradient T retarded minus T advanced inverse gradient T advanced. Yeah, I just take this T and I put it here. Lambda is just 1 minus 1, so I have two parts. It's the continuation here equals this thing equals this thing.
Stupid question, but usually when we think about the system with, for example, single particle Hamiltonian for the case of superconductivity, right?
Sorry, I believe this is not relevant for what I'm talking
The
about.
trace is
Trace?
just usual trace?
Yes,
or
just
like
usual trace.
Trace in space?
There is no number space, it's just a matrix of size 2n.
Okay, yeah, sorry. I thought that, yes, yes.
So, what is this? I mean, T inverse gradient of T. We already saw this before. Who can tell? This is a gradient of the logarithm. This is a gradient of the trace of the logarithm. And trace of the logarithm, as we also discussed, is the logarithm of determinant. So what is written here is minus 2 integral along the boundary of gradient of logarithm determinant TR divided by determinant TA. Right? And what is the integral of a gradient? We have a line integral, we integrate along the boundary, and the gradient is a vector object. Yeah, it has also a direction, so we have here is like the scalar product of two vectors. What is this? What will be the result of this integral? Hmm? Not, well, in some sense. Charge, yeah, well, actually it's just the difference. When you integrate a gradient along a line, you get the difference of the value on one end minus the value on the other end. And in this case, the line is the boundary. It comes back to the same point. So
But this is a logarithm.
it should be 0, but since this is a logarithm, it's a multi-valued function, it may happen that the argument, these determinants, they go back to the same value, but the logarithm does not come to the same value. It gets an extra number of 2 pi's. So in general, this whole thing should be equal 4 pi I times some integer number. This n is integer. Or you can think of it like this. TR is a unitary matrix. Determinant of the unitary matrix is just a phase. It's like exponent of I phase. And when we integrate the gradient, we just count how this phase changes along the line. And since we should come back to the same point where we started, this phase can rotate only by an integer number of rotations. So this I, it's like this logarithm is I phase. This I, and the phase rotates by 2 pi n. And the same for the advanced. So it's the difference of these two phases. So coming all the way back to the action, to the sigma model. Theta term, now the full theta term is sigma xy over 4 two-dimensional integral of trace of q nabla xq nabla yq. We have just proven that this thing is 4 pi I n. Something is missing. I'm sorry, this is wrong. This should be not 4 pi, this should be 8 pi. This should be 8 pi I n. At least it's written in my notes, but this is 8. And the reason for 8 is because we have these two TR and TA. And I believe there is an additional restrictions that these two determinants should be in some sense opposite to each other. We should have the total determinant of T should be 1. Determinant of the whole matrix T should be 1. Then determinant of TR is minus, is inverse determinant of TA. So this fraction is twice, it's like twice the logarithm of just TR, and then it's an extra 2.
It's not clear that it should be like that. It cannot be any other, like -1, for example. Determinant T cannot be -1.
Let me think.
Or any other way.
Determinant of T. Determinant of T should be 1. For some. Well, actually, let's discuss it separately. It's a tricky point, and I'm pretty sure that determinant of T should be fixed. You can fix it at any value, maybe, but it should be fixed so that the TR and TA are actually related. That's the point. That whenever you rotate the phase of TR, the phase of TA should rotate the same amount in the opposite direction.
The complete T, TR and TA together. Determinant of this thing also.
I can give you an answer to this question, but I believe it will only raise more questions, and we can go with this discussion quite far away. So a quick answer is the following. The Q matrix, the original one, is U2n divided by twice UN. This UN in the numerator can have any determinant. this product of two UNs in the denominator can also have any determinant. Actually, this determinant can be cancelled when we divide one by the other. So actually, we can say that Q, this is now only for Android. Nobody else, please pay attention to this. This is a very poisonous thing. So you can say it's SU2n divided by a strange object, which is UN times UN, with S applied to the product, if you understand what it means. SUN is the unitary matrix with unit determinant, and this is a product of two unitary matrices such that the product of their determinants is unity. This is the same manifold. I mean, nothing changed because this determinant in the numerator and in the denominator, they are just numbers, and they, when we divide one by the other, they cancel. So you can as well say that they were equal to 1 from originally. And this is the T matrix that you should use here. This one comes from the denominator, something that does not rotate lambda, and it should have determinant which is equal in total to 1. End of the explanation. I said it will raise even more questions, but you asked for it. Nobody else asked for it. So we can continue it later, okay? And please also remove it from the recording. Yeah. So this thing, I just know the correct answer, right? This thing should be a 2 pi I and an integer number. Oh, sorry. Times sigma xy. 2 pi I, sigma xy, and then an integer number. And this integer number actually depends on the Q matrix. I mean, depending on what your Q matrix does inside the sample, this whole integral can take any integer number. So there are configurations of Q that give you 0. There are configurations of Q that give you 1 or -1 or 2 or -2 or any integer number. And in some context, this number is also called topological charge. This is topological charge. Why it is a topological charge, we will discuss in a minute. Topological charge. This object has a very clear geometric meaning, and you can check that all the coefficients are correct without doing all this nasty business with special unitary matrices. This is a topological charge. So each configuration of Q is assigned a certain integer number. Now it's very much clear why this term does not contribute to any equations of motion. If you take a variation of this function, you apply small variation of Q, this function cannot change because it's an integer. Integer cannot have a small change. It can change only by 1 or -1 or 2. It cannot change infinitely small. So if you change Q a little bit, this thing remains the same constant. That's why variation of this term is 0. And it does not contribute to any equations of motion. Very nice. This also means that this term is almost doesn't contribute to anything. It's just a number. You added a number to your action, which is almost a constant. It should not change much. But as it turns out, it does change something. This object is very much topological, and it leads exactly to the quantization of whole conductivity. So let's I promised to explain why this is called a topological charge. So the explanation is easy. Your Q matrix, our Q matrix, depends on X and Y, right? So what does this Q matrix do? We have our real space, our two-dimensional space. X and Y live in this two-dimensional space. Any point has coordinates X and Y, X and Y. And this pair of coordinates is mapped, this q of xy is a function. It maps the point xy into the value of q. And the value of q is also a point, but not in real space, is a point in this symmetric space, in this manifold of all q matrices. So it maps into this u to n over twice un space. Now, what happened when I say that I want my boundary condition, I want my Q matrix to be equal to some constant at the boundary. This is my real space. And at the whole boundary, along this whole line, Q matrix takes one particular value. It means that all points at this boundary, every point, is mapped onto the same point in the space of Q matrices. So each point of this boundary is mapped onto the same point as if this whole boundary was only one point in real space. Yeah, just imagine I will now take my real space, erase this. I still learn how to erase with the hand. And instead of just a plain two-dimensional square, I will draw the sphere. Sphere is also a two-dimensional object, but it doesn't have a boundary. So in a sense, I say, let's take our two-dimensional plane and make it a sphere such that the infinite point on our, or boundary point on our plane is, for example, some point on this sphere. And this point will be mapped to wherever. Like, this is a very standard thing you can use. It's called a stereographic projection, for example, how to map the plane onto a sphere such that the infinite boundary of this plane is mapped to a single point. So our Q matrix does exactly this. It takes real space in the form of a two-dimensional sphere S2 and maps it into this manifold. Maps it into this manifold. And each map of this type from a sphere into a manifold, each map is characterized by an integer number. So n, this characteristic, equals degree of the map. Degree of this map. How many of you know the term degree of the map? Andrei, what is degree of the map? What is degree? What is degree of the map?
How many times one point is mapped to its
How many times a certain point is covered? How many points are mapped to a given one? For example, map of degree 1 means a one-to-one map. Each point is covered only once. Map of degree 2 means each point in the target space is covered twice. So there are 2 points in the original space that are mapped to the same point in the final space. Degree 3 means there are 3 different points in the original space that are mapped to a single point in the final space. Degree of the map is a constant, it's an integer number, and it's a constant because if some point is covered by 3 different points from here, then the vicinity of this point is covered by vicinities of these 3 points, which means that any neighboring point is also covered the same number of times. So it doesn't depend on which point you look at. If one point is covered 3 times, it means the whole manifold is covered 3 times. If one point is covered 5 times, that means that the whole manifold is covered 5 times. Example. Imagine this particular case. So we have a map from S2. S2 is a two-dimensional sphere. S2, imagine we map S2 into the manifold. Let's fix number of replicas equals 1, just for simplicity. U equals 1. U2 divided by twice U1. What is this manifold? This is a sphere. This is the same sphere. It's just S2 as well. it's a matrix. Look, this is a matrix. It's a 2 by 2 matrix. Yeah, U2, 2 by 2 matrix, which squares to 1. It's like our Q matrix is just a 2 by 2 matrix. Just example, Q is T inverse lambda T, and lambda T is sigma Z. I mean, sigma Z is just a Pauli matrix, 1, 0, 0, minus 1. We have a 2 by 2 matrix, and we rotate it by unitary rotation, which is also 2 by 2, by the group U2 rotated. So what we get? We get, this is not a sigma Z, it's not a Pauli matrix in Z direction, it's now a Pauli matrix that points in any direction. So what we get is a unit vector n times the vector sigma. Sigma is now sigma x, sigma y, sigma z, 3 Pauli matrices. This is sigma z. After this rotation, we have a Pauli matrix that is the combination of sigma x, sigma y, and sigma z, and the coefficients form a unit vector. And this unit vector lives on a sphere. So this manifold, this Q matrix from this manifold, can be described by just a point of a usual sphere. And I keep showing you this picture that you can always think of the manifold of the sigma model as some type of a sphere. This symmetric space is like a sphere in some general sense. So this one is literally a sphere. There is no any special sense. It's literally a sphere. It's just some weird representation of a sphere. Maybe not weird. So what we do, we map a sphere, which is our real space, into exactly the same sphere as our target space. So now, what is the degree of the map? Imagine we map the whole sphere, all points of our original space, into a single point in the target space. Q matrix equals lambda everywhere. Everywhere in our sample, Q equals lambda. It's one configuration of Q, yeah? The most boring one. It means that all points of the original space, of the real space, all these xy points, are mapped to this sphere into point sigma z, lambda, just 1 point. This is a map of degree 0. Each point in the target space is covered 0 times, well, except for the North Pole, but who cares? I mean,
If we just map it from 1 point to 1 point,
look,
cover each
I have one sphere, and I have the second sphere, and I have a continuous map from here to here. Continuous means that 2 close points should be mapped to 2 close points. And now I take this whole sphere, every point on this whole sphere, and map it into a single point on this sphere, just all of them here. This is the map of degree 0. N equals 0, I can calculate it without anything. If Q is constant, all gradients of Q are 0, the integral of all gradients is 0, the theta term is 0, degree of the map is 0.
It just means that Qxy equals to lambda.
Yes, for every x and y. This is what I said from the beginning. Q is the constant in the whole space. Then there is a different type of map, which is a one-to-one map. I take my sphere and I map each point to the same point in the target space, 1 to 1. And this is a map of degree 1. Then there is, for example, a map of degree 2 when you take the upper hemisphere, this north hemisphere, and you map it on the whole sphere here, such that the equator becomes the south pole. You just do this, and you do the same with the southern hemisphere. You map it on the whole thing, and then at the south pole, this equator is matched from the two things. This is a map of degree 2. And actually, you can have map with any integer degree like this. There is another example, not this one, much easier. Imagine we map not a sphere to sphere, imagine we map a circle onto a circle. Oops. Circle onto a circle. It's the same story. If we map the whole circle into a single point, this is map of degree 0. If we map a circle into a circle, 1 to 1, it's the map of degree 1. And actually we can map a circle into a circle with any winding. So as we go around this circle, we can go 5 times around this one, or minus 5 in the opposite direction. So it's the same story. Degree of the map is the integer number, which takes any integer value, from minus large number to a plus large number. So what this topological term does, it counts the degree of the map. And for this particular example, this is a personal homework for Andrei. Take this Q matrix, calculate theta top with gradients, and prove that the map of degree 1 will give you 1 with a proper number 8 or 4 in the prefactor. Okay, so once again, this is an important statement. Topological charge, or in other words, it's a synonym. This one, degree of the map from real space into target space, into the space of the sigma model. It's this one. Is it clear? I mean, the geometry of this thing. Yeah.
Why is real space a sphere?
Why? The real space is a sphere. It's not literally a sphere, but it behaves like a sphere because we impose boundary conditions that at the boundary, Q matrix takes one particular value. This is arbitrary, and also in this sphere there is no any point that is actually. So imagine how to say this.
But then it depends on our boundary conditions to be overnight.
No, it doesn't. That's the point. If our real space is this table, this is a table, yeah? And we say the whole boundary, each point at the boundary, Q matrix takes the same value. And say this value is Q0, some particular matrix. It means that in this picture, the south pole of the sphere, the south pole corresponds to the boundary. If we do stereographic projection, the south pole is mapped into this particular point Q0. Doesn't matter which one, just to some single point. This one is mapped to here. And then the whole sphere is mapped to the whole sphere.
Yeah, but then you can say real space is any compact manifold.
Yeah, and to the, well, the sphere.
Specification will be different.
No, wait. Once again. If I say that my boundary is a single point, is mapped to a single point, I can as well assume that in real space it was a single point.
Then you assume that your boundary is a single point.
Yes. And this makes my real space a sphere. If I identify all points of the boundary, I make from a plane a sphere.
Why does it make sense to identify all the boundary at the same point?
I'm just saying that if the boundary conditions are such that Q matrix is fixed at the boundary, fixed at one particular value.
But do we have justification for that? Because then the decision on boundary conditions.
Justification is rather vague, but okay, I can say also this way. Imagine we have just very large real space. 1 kilometer by 1 kilometer. So if the Q matrix is not constant at the boundary, it means the gradients of Q will not decay even on the distance of 1 kilometer, which means the total action will be very large because the action, there is also the first term in the action gradient of Q squared integrated over the whole space. So it's very unfavorable to have these gradients finite on a large area. So it's like it's a limiting procedure. We have a sample of finite size. We take into account all possible configurations of Q. But then as our sample gets larger and larger, we should eventually discard the configurations that, so we should consider only configurations that do not have gradients far away, because they will have very large action. And as long as Q doesn't have gradients far away, it's the same as saying that Q is constant far away. Well, again, it's not a rigorous argument, it's just some vague justification. And in fact, there are examples when this is not the case. So we will not consider them. I'm just saying that this thing is correct for infinitely large samples. So if formally your two-dimensional system is infinite, this will be correct. Because in an infinite system, in order to have a finite action, you have to assume that all the gradients of Q are bound to some finite volume, and then they decay at infinity fast enough. And then at infinity, it's a constant.
But if you take periodic boundary condition,
Then it will be wrong. So if you study quantum Hall effect on a two-dimensional electron gas with periodic boundary conditions, you may have a different result. This is what I meant. So there are examples that do not behave like this. We will not go deep into that. Actually, it's not that much different, but the justification should be different. Yeah, so for example, you can have periodic boundary conditions on a torus. I mean, this equals boundary to this and that one to that. Then you map not a sphere, but you map a torus into target space, and the homotopy is quite different, and that's another story. I really don't want to go into that particular case, but you're right. What we are doing here literally applies only to just very large or ideally infinite two-dimensional planes. Okay, so where did I stop? Degree of the map, topological charge, integer number. This is all different things that we say about this theta term. So what can we conclude? Look, the action of our sigma model now becomes the action of Q is integral two-dimensional trace sigma xx over 8 gradient Q squared plus 2 pi I sigma xy n of Q. It's just the same action. But now this theta term is written as a degree of the map, as an integer number. As a, yeah.
Maybe at this point repeat the same question that like we are dealing with quantum Hall effect, we want to describe physics and we get this model. So maybe on this stage we can explain why you didn't write immediately this model.
Sorry. Sorry. Can you ask again why we did what?
Yeah, so like we start with physical effect that we
Yeah.
remember from school or something. We want to describe it in a
Yes.
more advanced way. And we
Yes.
start immediately with this model. I asked why. You said because there is some consequences
Which I will right now tell,
Okay, thank you.
and you will see it. So actually it can be derived. I mean, I could have started with a Hamiltonian and derive this action with this term. The Hamiltonian for two-dimensional electrons in magnetic field, there is the derivation, but it's very technical, much harder than without magnetic field. And instead, I just show you what the result is, and now I will show you what the consequences of this is, and you will see that it looks plausible. So the consequences before. When we didn't have this term, without magnetic field, we had only one parameter in our sigma model. The sigma xx was the single parameter of the model. And then there was an RG equations. There was a renormalization of this model that told us how this sigma changes with the scale, and this was this scaling law for localization. Sigma xx was decreasing with increasing the size, which is called localization. No two-dimensional metals. Everything is an insulator. We discussed this. Now we have two terms in the action, sigma xx and sigma xy. If we now do renormalization of this action, which Pruskin also did, what we get is a two-parameter scaling. Two-parameter scaling. Two-parameter scaling means we have some beta functions for both quantities sigma xx and sigma xy, and two parameter scaling in this two-dimensional parameter space of sigma xx and sigma xy. Should be some. We will not derive it from this action. This is even worse than deriving the action itself. What we do instead, we will list a few properties. Property number one, this two parameter scaling, some two parameter scaling law should be periodic in sigma xy, right? If I add any integer number to sigma xy, I will change sigma xy to sigma xy plus 1. No consequences, because it will add to my action only 2 pi I times integer number, and the action stays in the exponent. Partition function is the exponent of the action, so adding 2 pi I integer number doesn't change the exponent. That's why adding any integer number to sigma xy has no observable consequences. I can even write it with period 1. Second, imagine sigma xy is 0. There is no magnetic field, sigma xy is 0. This case was already started, and we saw that there is a localization. Sigma xx flows to 0. Yeah. Remember, there was this beta function which starts with minus negative 1 over sigma, and then go. And the sigma xy will not appear. I mean, if there is no magnetic field, we have this action. Without that term will never appear. So the second thing is the following: localization, full localization at any integer value of sigma xy. Sigma xy equal to 0, we know there is a localization, but also we know that if we add any integer number to sigma xy, nothing changes. So this localization should happen for all integer values of sigma xy.
Why localization at sigma xy equals to 0?
Because the system without magnetic field has sigma xy equals to 0, and we already started it, unitary class, only sigma xx, single parameter scaling, sigma xx flows to 0, localization. And the same should happen at any integer value of sigma xy. And the third property, which probably should have been the second, but doesn't matter, the third property, it's not only periodic in sigma xy with period 1, it should be also invariant. This two parameter scaling should be invariant under sigma xy changing to minus sigma xy. Because, why? Because who cares if magnetic field is up or down? It's just a two-dimensional. We just flip our two-dimensional sample. Nothing changes. So, from these three properties, the two parameter scaling picture can be actually guessed without calculation. And this was done around the year 1986 or 7 by some other people who saw this work by Pruskin. So I will just now show you what happens. What is a two parameter scaling? We have a plane which is sigma xx here and sigma xy here. And we have a sample with a certain value of sigma xx and sigma xy, so there is some point in this plane. Then we start increasing the size of the sample, and according to scaling hypothesis or to renormalization of the sigma model, both parameters somehow change. So there is a flow, there is some line how this two parameter, there are some trajectories on this plane, how they change. For example, if sigma xy equals 0, if we are on this point, on this line, where only sigma xx is present, the flow is downwards. The flow flows downwards all the way to 0. And this is exactly the case we studied before. When there was no magnetic field, everything, there is a localization, there are weak localization corrections, so we start with large sigma, there are negative corrections, it flows, and eventually we end up in the insulating state, which has 0 conductivity. And the same thing, according to these rules, the same thing should happen at every integer value of sigma xy. So we should have exactly the same flow all the way to 0 for sigma xy equals 1, exactly the same flow all the way to 0 for sigma xy equals 2, and for sigma xy equals 3, and so on. So along these lines, if we start our flow with some value of sigma xx and an integer value of sigma xy, it should flow exactly vertically. Sigma xx decays, sigma xy is fixed and doesn't change. Either 0 or any other integer number. That's all. I mean, from these properties you cannot draw much more. But then, if you know what a quantum Hall effect is, this is actually what happens. This is the true flow diagram. I will first draw it and then discuss why it has this form. So it's periodic, as was suggested. Each interval from 0 to 1 and from 1 to 2 are exactly the same, and from 2 to 3. And it has a mirror symmetry. If you flip the sign of sigma, nothing changes. I mean, around 0 it is symmetric, and also around any other integer point it is symmetric. But what exactly happens inside is not that much. It does not follow from this general principle. It already requires some calculation. So what Pruiskin did, he actually calculated the beta functions for sigma xx and sigma xy from his model, and he found that for sigma xx it's just negative. It's almost the same as it was without magnetic field. Sigma xx just goes down. And we have this flow which flows down more or less for all values of sigma xy. But there is also correction to sigma xy, which is periodic. The beta function has some cosine of sigma xy inside, and it's such that these flows, they are diverted towards these integer values. I mean, it doesn't just flow vertically, it is diverted towards the nearest integer value. And there is a very specific case when you have a flow with half integer value of sigma xy, exactly between two integer values, you end up at some point where the beta function is 0. It cannot decide whether to turn left or to turn right. And this point where, so your flow actually stops at this point. And this point where it stops has exactly half integer value of sigma xy and has some finite value of sigma xx. And this point has a name. This point, well, it's repeated in each period.
It looks unstable.
It's unstable in this direction, but it's a point of 0. I mean, if you deviate a little bit, then you will.
Yeah, so it looks that it's hard to find this point experimentally.
That's very easy. I mean, there are many experiments. Any experiment of quantum Hall effect does this for you.
Because usually unstable points are not observable.
Or any unstable points are known to describe phase transitions. Whenever you observe a phase transition, there is an unstable fixed point. And this point has a name, which is the quantum Hall effect critical point, or a fixed point corresponding to the quantum Hall transition. And quantum Hall transition is a phase transition between two integer values of sigma xy. Now, if I scroll this whole thing back to the very first picture, sigma xy with these steps, each step is actually when we flow to one of these integer numbers. Each step is an insulator. Sigma xx is 0. Sigma xy is integer. It's a quantum Hall insulator. There are different insulating phases that are characterized by integer values of sigma xy. They are called quantum Hall plateaus. And between these phases, there are phase transitions when you go from one integer value to the other one. And this is where you have this step. Sigma xy goes from one integer value to the other integer value. And exactly at this step, when you are in the middle, sigma xx is not 0. It's not an insulating state. It's a critical state with a finite value of sigma xx, which signifies that not all states are localized. This is what I say from the very beginning. When you approach the middle of the Landau level, there is a delocalized state there. Therefore, the system is not insulating. It still has some longitudinal conductivity at this point. So whenever you observe in the experiment the step from sigma y1 to 2, in the middle of this step, you are in this critical state. Of course, it's unstable, which means if you go a little bit to the left or to the right, you go to one of the stable points, which are insulating, which are these two values. But if you do, for example, measurement at finite temperature, which will limit your, will introduce an infrared cutoff, at any finite temperature, this step has a finite width. You lower the temperature, it becomes sharper and sharper. It's a certain law how this depends on temperature. This law is called whatever dynamic exponent. It's a critical exponent of this critical point. So you can measure it experimentally and investigate the vicinity of this point. So it's actually the same. It's exactly the same as in any other phase transition. So it's quantum Hall critical point, which describes phase transition between two insulating phases with two adjacent integer values of sigma xy, or between two. I should probably draw this somehow. So it's the picture that we started with. It's concentration and sigma xy. And the picture is like this. It's 0, then 1, then 2, then 3. And each step here, so each state, each horizontal line is an insulator. Why is it an insulator? Because I should also draw here sigma xx. Sigma xx is the red curve, and sigma xx looks like this. It's 0, and then it has a peak. 0, then it has a peak. 0, then it has a peak. It's, oops, sorry, it should be the same peak. It has a peak at every transition point. Okay, my hand does not erase anymore. So it's a peak around every integer point. These are, I don't know, these are 0, 1, 2 on the axis of sigma xy. And for sigma xx, there is some finite value of sigma xx at each maximum, which corresponds to this value. Yeah? It's sigma xx and xx. So sigma xx critical value, sigma xx critical value is approximately 0.6. It's an experimental knowledge. We cannot derive it from the sigma model, but we can do the experiment.
This is the universal cone.
Yes, this is the height of this dome.
Doesn't depend on material.
Yes, it's universal, doesn't depend on material. It's a consequence of the sigma model, which knows nothing about your material, just sigma xx and sigma xy. So now these peaks in sigma xx and the steps in sigma xy, actually they are not vertical. Yeah, these steps, they have some width which depends on temperature. The lower the temperature, the sharper is the transition, and also the narrow is this peak in sigma xx. But the height is temperature independent, it's this critical value, and the width, its dependence on temperature is some power law which is related to the critical exponents near this point. So this is the proper theory of quantum Hall effect. I mean, in order to describe quantization of sigma xy, you need disorder to localize all the other states except for the single state here. And to demonstrate that the single state does not localize, you should add a theta term to the action, otherwise you will just localize everything. So this theta term does almost nothing. It almost changes almost nothing in this theory. It's a very weak thing. It is total derivative. It's an integer number. It's integer number times 2 pi I and times sigma xy. So it almost changes nothing. It becomes relevant only somewhere here near the, when sigma xx is already small. And the only thing it does, it prevents localization of a single state whenever sigma xy is exactly half integer. Whenever sigma xy is not half integer, it will just, yeah, it will tell you that everything should be localized. So it will have almost no effect. So that's it. I mean, that's it about quantum Hall effect. Now we have time for plenty of questions on this topic.
I have a general question.
About quantum Hall effect. Okay.
So suppose I'm in school in 10th grade and I learned classical philosophy.
Okay.
I can ask, like, that's how nature behaves, so nothing what we've seen right now. And if I asked, for example, someone, what's like that, you say that something is not like a seed, and why is it so? And they would say, oh, because there are some quantum effects that you haven't considered. But can you give a better answer? Not like some quantum effects, but what people in classical Hall effect miss so that they can't see that actually there is this quantization?
They miss quantum effects which are responsible for localization.
Yeah, but like when, okay, quantum effects, okay, we have like black body radiation, Planck's constant, so it's not obvious how to plug these two ideas and get these results that we have discussed.
Well, that's probably the reason why quantum Hall effect was first discovered experimentally and only then explained theoretically.
Yeah, now we have theories, so now maybe we can have.
Now we know how it works. I mean, what's your problem? I mean, we already know the answer.
Yeah, but then the classical Hall effect, that's quantization of photons, of
Yeah, and we have a theory which tells us that in classical limit, no quantum corrections, we are somewhere up here, sigma xx is large, and sigma xy takes any value you like, it's a classical Hall effect. And then, as you take into account quantum effects, you have this flow that gradually collects all the quantum corrections to sigma xx and sigma xy, and it leads you to the quantized picture.
Is it like having flow doesn't mean that we have something quantized?
Yeah, it doesn't mean that. It means that you have to sit down, solve the problem, and see what it leads to, and it leads to this. I mean,
So maybe we haven't used much quantum.
oh, it's a lot of quantum ideas here because this whole flow is the result of quantum corrections. They do not exist in classical physics. Localization does not exist in classical physics. If you have some weak disorder, some impurities that are very weak, and your electrons have huge Fermi energy, they will never be localized classically. but in 2 dimensions, they scatter on these weak, small impurities, and these different scatter and different trajectories, they interfere. This is a quantum effect, and this interference leads to localization. So eventually, this electron that has huge energy and it doesn't really care about these small impurities that it almost doesn't see, eventually it gets trapped by the collective action of many impurities, which is the result of quantum mechanics. It's a fully quantum effect. And if this electron, which is get trapped by many impurities, it says everything is localized, I cannot do anything, I cannot carry any current. If it also has a magnetic field, it turns out that for certain energies, only very specific energies, this electron is not completely localized. So this is a quantum effect on top of quantum effect. What else? What else quantum would you like?
Let's assume that n is a very large number. How to see that the limit of sigma xy goes to the classical answer? With
This one?
magnetic field? Yes.
Oh, I didn't tell you how it depends on magnetic field in this picture. That's why you cannot see it from here. But if you are Prussian, if you derive the sigma model starting from the Hamiltonian, you will derive this theta term, and as a prefactor in front will not be a letter sigma xy, will be some expressions of parameters of your Hamiltonian, which actually equals Kubo formula for whole conductivity. So you say, aha, this is the sigma xy here, but I have never shown you the Kubo formula for whole conductivity, also for a good reason, because it's not so simple. And again, it's a technical thing. Sigma xx is easier than sigma xy.
Okay, so at limit of the large n's, these prefactors will become not just sigma
Look,
xy, right?
look. The first prefactor in the first term was not sigma xx, it was pi nu d over 4. We derived it. And then we say, aha, but this is the same as sigma xx, or just sigma. So the same way, when you derive a magnetic field, you have the second term, and the prefactor is not pi nu d over 4, it's magnetic field divided by concentration, and blah, blah, blah. And you say, aha, but this is sigma xy.
Okay, yeah, but it just means that the model will be still applicable, but the coefficient near this topological term will be just not sigma xy, and it will have some different physical meaning, right?
Oh, that's a tough question. Actually, look, I probably can give a separate lecture about this. We derive the sigma model, and we find this thing pi nu d over 4. And we say, this is sigma xx. Then we say, let's take the sigma model and renormalize it. And this object will be renormalized. There are some corrections to it. So after we renormalize it to some extent, for example, it gets twice smaller. Yeah? According to this flow, it flowed twice smaller. Then you come and ask me, please prove to me that this is still sigma and not anything else. And I will tell you, okay, to prove this, I should do a measurement at this scale. So I should add to my action a source term which will measure sigma xx, not the coefficient in front of the gradient, but the real conductivity. And then it can be proven that it is the real conductivity. I mean, this thing that we renormalize is the conductivity, but it requires additional calculation. And the same for sigma xy. And actually, this calculation is only correct for large values of sigma xy. It's not correct near this 1 to 3. It's correct near 10, 20, 30. So near these points, it might happen that sigma xy as the parameter in the action is not the same sigma xy as you measure in the experiment. But there are some extra arguments that, for example, there is a Laughlin argument about this that proves you that this quantization should occur in the original sigma xy the same way it occurs in this term, in the sigma model.
Okay, so for large n, this parameter
Is correct. For large n, this is correct.
This
For small n, it's trickier, but it is still correct.
But it should still work because we just derived this renorm group with just two coefficients, sigma and
Yeah.
and sigma y, and it works.
Yep.
For any n.
Yep.
Yeah, there is no
It doesn't
magnetic
care.
field.
I mean, it's periodic, whatever
Yeah,
n you
yeah.
like.
So even for very large.
Yeah.
But so this means but you're telling me that at large n it doesn't work. So it
No, no, no.
at large n
I said
this
just
parameter
the
is-
opposite. At large n, it works better than at small n. At large n, I can prove that this is the measurable sigma xy, and at small n, it's harder to prove. That's it. It's still the measurable sigma xy, it's just harder to prove, but I haven't shown you the proof for small or large sigma xy anyway, so I say I can give a separate lecture how you derive it. It's correct. I mean, the things shown here are correct, just the way I presented them is not fully convincing, maybe because I didn't do this derivation.
So you want to say that even
I'm sorry.
large n's for classical
I said for the
answer,
third
it
and
still will be
yes,
steps.
yes.
Okay, good.
But for large n, you will start with a larger value of sigma xx, because it's also proportional to n, to the total density, and you need much larger scales to flow all the way down to 0. That's why it's harder to observe.
Okay, good.
Can you calculate the critical exponents from the sigma model?
Actually, I cannot, and actually nobody can. Nobody can, because all the calculations within the sigma model that we did, which are weak localization corrections, they were perturbation theory in large G, or in large sigma, so they all are correct somewhere far up on this plot. But for sigma close to 1, this perturbation theory doesn't work. Therefore, this value, as well as critical exponents, for example, there is a very important critical exponent called nu, which tell you how fast you deviate from this point. I mean, how fast this flow, how much unstable it is. And this exponent is responsible for what is called localization length exponent at this point. So there is a single state which is delocalized in the middle. If you are close to the middle, but not exactly, your state will be localized, but localization length will be very large. And this localization length diverges as you approach here, and this divergence has this exponent nu. There are just some numerics that calculate this. It's the only way.
Calculating this.
Oh,
Yeah.
very nice. So you know better than me.
Yeah, but I was interested in that. If you can do it from here, yeah.
I can do perturbation theory in a large parameter 0.6, so it will not be very reliable.
Do you know any other I mean, there are multiple approaches how to describe quantum Hall effect. For example, these network models, these choker.
Yeah. Choker quantum network models, these are mainly the numerical approach. I mean,
Yeah.
they are used to model. It's, well, again, you probably know it better than me. It's a semi-classical model that has the same symmetry. So according to our universality statement, it should describe the same critical point. And it also is designed such that you don't need extremely large scales to localize everything. So you start somewhere already close to this point. And but again, this is just a numerical. It's some model Hamiltonian that has half integer sigma xy and embedded there, and that's why it can directly give you the properties of this point. There are other theoretical tools, not numerical, I mean analytical. So there are some speculations that since this is a critical point, it should have some extended symmetry. Namely, somebody says that all two-dimensional critical points have, I forgot the word. I forgot the word in all languages. What's this special field theory that applies to any two-dimensional critical? Sorry? No. No, conformal, yeah. It should be some extended theory that has a conformal symmetry, and there are speculations that this is a conformal theory with a central charge equal to this, because we know from numerics that the localization length exponent is 7/3, so this looks like the central charge 5, I don't remember. And then people, so there are many speculations, nothing rigorous so far, and no big hope to do it analytically in any future. Yeah.
So the sigma model is the only way how to analytically obtain or the best way?
It's I'm not saying it's the best or it's qualitative in the sense that we do the calculation within the sigma model and we see this periodicity, but we cannot really resolve the exact numbers around so the exact value of this, the height of this dome or the shape of this thing. We just see the periodicity and we see the tendency that goes from large sigma xx, how this thing.
But then so method is complicated, so there are no more simple methods to get same result.
For this flow, no, it's the only one.
This flow is crucial to understand the flow.
This flow is an explanation why you have the quantum Hall effect in the first place, why it's quantized. You see, it is quantized because it flows to quantized numbers. That's it. I mean, if there is no such a flow, why would this thing be quantized?
So that's the best way how to explain it.
This is a way. I don't know if it's the best one. It's the best one that I know. Maybe you know the better one. I'm not an expert in all possible explanations. Okay, so actually we don't have much time left, so I will not start a new topic today. And instead, I just want to repeat once again what I said. This is a very important thing. This is the first, really the first lecture where we encounter something topological. And this topological thing in the sigma model language means that we have a topological term which measures the degree of the map from real space to the space of Q matrices. This degree of the map can be written as some integral of gradients of Q matrix. And now to the question asked on the very first lecture. There are manifolds that, not on the very first lecture, on the very beginning of this lecture. How do we know that we should include this theta term? I say because we are in the unitary class and we have this manifold U divided by U. Now imagine you are in the orthogonal class and you want to include the same thing. Orthogonal class has a different manifold. And it turns out that in 2 dimensions, you can map whatever you like from the real space to orthogonal class, but the degree of the map will always be 0. I mean, there are no maps with a non-trivial degree. This statement is said in different words like this. Second homotopy group of the target manifold is trivial for orthogonal class and is the Z group for unitary class. That's why we can include this term in the unitary class, and we can also include it in the orthogonal class, but it will be just 0.
Should we add physically to our system to make our class from unitary to orthogonal?
Sorry?
What we should add to the Hamiltonian to our system as a quantum Hall effect to make this class orthogonal?
Oh, nothing, because orthogonal class requires time reversal symmetry and it is already broken. Whatever you add, you will not restore time reversal symmetry.
Okay, so we should remove magnetic field.
Yeah, you should switch off magnetic field.
And we will not have a quantum
course. So, homotopy group, it's exactly what we discussed for the good part of this lecture. Homotopy group of any manifold pi d of m is a group. Doesn't matter if it's group or non-group, that doesn't matter. It's degree, how you say it? Gesundheit in German, but yeah. Degree of the map from d-dimensional sphere into the manifold M. Imagine you have a d-dimensional sphere. It can be 1-dimensional, 2-dimensional, 3-dimensional, 8-dimensional. And you have some manifold M. And you have different maps from this sphere to that manifold. Continuous maps. Then these continuous maps can be continuously deformed. And you say all the maps that can be deformed into each other are equivalent. And these maps that are equivalent can be crudely identified by the degree of the map, because when you continuously modify it, the degree doesn't change. So if you have many non-trivial maps that cannot be deformed into each other, you have a non-trivial homotopy group. And the statement is the homotopy group with the index 2, two-dimensional sphere, of the manifold u to n divided by twice un equals how much? Z. Group of all integer numbers. Because all these maps are characterized by a single integer invariant. Or you can combine all equivalent maps into a single thing, and these single things will be numbered by an integer number. But if you compute pi2 of a manifold of an orthogonal class, it will be 0. No, the group is trivial. I mean, group of one element. All mappings are equivalent, can be transformed one into the other. And you can check it. You have a second homework. You take a Q matrix from the orthogonal class, and you compute this Prussian term Q, nabla Q, nabla Q. Well, it's a joke. I mean, you don't have to do this. There is an additional symmetry that T matrix is not unitary, it's now orthogonal or symplectic. Symplectic, actually, in the case of orthogonal class. But so it's like this matrix equals its transpose. I mean, T inverse equals T transpose, for example. And then you have this trace of T inverse T with many nablas. And you say the trace doesn't change if I transpose it. But if you apply this transposition and use your symmetry, you will see that this topological term changes sign. So you prove that this thing equals to minus the same thing, which means it equals to 0 for any configuration. Okay? Yeah.
Very simple question. We have retarded and advanced sectors.
Yes.
They are nearly the same.
Yes.
First of all, where we actually couldn't we do all of this absolutely the same, even without advanced sector?
No.
Why?
Because if you have only retarded sector, your matrix lambda is only ones but no minus ones. And when you try to rotate it, it remains 1. So the whole Q matrix is 1, and your whole manifold is just single point. And your sigma model does not exist.
Okay, then the same question from the other side. What is the connection between retarded and advanced?
They are not actually separate sectors. They are connected by these rotations with the T matrix. I mean, your Q matrix does not split into these sectors. Look,
Okay, yes,
for-
yes.
for-
I understood. Okay.
for one replica, you have this sphere.
Yes.
Yeah, the whole Q matrix lives on the sphere. There are no sectors. But if you start with only retarded, you cannot generate the sphere. So to generate it, you need this discrepancy between.
Well, and I have a kind of question not about the quantum Hall effect, but about the sigma.
Okay. Yeah.
Actually, we derived sigma model for specific numbers of replics. But when we are trying to calculate some corrections, we never use this parameter of number of replics, and we are just imagine that our Q matrix is living in one replic.
Not necessarily one in any, and just one for unitary class and for one replica. I can really imagine what this manifold is. For other classes, or for this class with 5 replicas, it's a 50-dimensional manifold, and I cannot imagine it that clear. But yeah, I should say probably that the lecture is actually finished. I mean, you don't need to sit and listen to all my answers. Thank you.